Okay, we're being live streamed.
They should just shoot their assigned project leader a message, because a lot of our pods are happening online anyway because our TAs have COVID.
Yeah.
So I think that's the best way to do it. And if someone's really sick, they
Okay, I'm getting echo from someone. Let's see.
Can you make me a host as well?
Okay. That should work, yes. That should work in theory.
Hello.
Okay, we should be live and in color, I think. We're still early. We're gonna wait a second before we start.
Not much color for you.
No, I'm in black and white today. You cannot see the screen yet. That's true. It is video muted. Now it's unmuted. I still need to share my screen. Share screen. Okay, how's that look? Okay, should we start?
Yeah, let's go.
Okay, it's the end, it's the end. So what we want to do today, firstly, is just mention administratively, lots of people are getting COVID, life is crappy. Although no one that I know is going to the hospital this round, which is really good. So just check for your TAs with your pods for the presentations. Lots of things will be online. Lots of 2 TAs already have COVID this week. I hear it's very popular these days. So just stay in touch with your TA. We'll work things out. Any bureaucratic questions or remote people? Cool. So what Conrad and I want to do is to say, I want to say a few things about what's happening right now in 2022 in deep learning as a preference to really talking about the future.
That's right. Yeah. It's going to be different.
Okay. So what's big right now? Multimodal stuff. So everybody's putting out stuff that is speech, vision, text, everything put together, combined with often modules that here's the speech input, here's the vision input, which looks like a CNN, here's the language input, which looks like a transformer, oh, except they're all becoming transformers. Trying to combine them together. Lots of drug discovery, but I think I don't want to talk about it, but it's sort of cool that there's lots of people designing drugs and doing QSAR relations and cool things. Lots of combined architectures. So things that you could easily do now but haven't seen. One of my favorite current ones is a conformer. You have speech as an input, audio input. The speech signal gets put into a CNN and then embedded, and that's then sent to a transformer, which captures the long-range dependency. So one thing you should take away from this course, lots of mixing and matching of different pieces.
And in a way, that's the cool thing about deep learning, because we have a language in which we can combine all these pieces, which is gradients. So we can basically glue together anything we want and combine all the advantages of the different approaches.
Cool. And if you look at sort of a modern conformer, a wave to vec, what you see is all the things we've seen: self-supervised training, convolutional layers, probably an optional quantization where you map the vectors to cluster them into groups, a transformer component, and then a supervised fine tuning where you then readjust at the end. So lots of these things are combining all the pieces you've seen in this course. Combinations of unlabeled data, self-supervised, learning a embedding of speech. How do you go from sound to an embedding? Then a smaller amount of labeled data, supervised fine tuning, mapping the speech onto words. Make sense as an architecture? And again, this idea, there's lots of ways to mix and match these. One in my area, the language models for dialogue applications, Lambda. Again, the same idea. Transformer, self-supervised, crap loads of data, or Google here, take lots of data, build a model, then tune it up with some sort of labels. Something which is maybe some sort of a context, a question is a conversation, what's up? Something which is how someone would respond, not much. And then some sort of a human label. It's sensible, it's interesting, it's grammatical, it's polite, it's rude. Lots of worrying about these things. All the systems we build for conversation agents, you train them on Reddit, and what do they start doing when they have a conversation?
They're trolling you, of course.
They're trolling you. They're misogynist bastards, right? So the big companies, I'm talking here, Google and Amazon and such, are spending huge amounts of effort because every time they train up a nice model, it reflects the world. And that turns out not to be the image that they mostly want to project.
So, but that's clearly the big problem with all those models. Is there even a solution? Not like it.
Well, so one solution that people are trying is they take a bunch of conversations, get humans to label them as unsafe, and then fine tune the model such that it tries to not produce unsafe things. So they're trying to do is put some sort of a feedback, right? That as people go, and they're paying lots of people label this is an unsafe or rude remark, it then tries to gradient descend away from them.
But there's lots of rude remarks that are extremely context sensitive and difficult. How can we hope that this will ever solve it?
And so a lot of people, we should talk by Martin Sapp, who worked for me and now is starting at CMU. And he's been training context sensitive models to recognize who's saying what to what. Famously, use the N-word. If I use the N-word, this is not okay. But there's lots of times when that's a bonding thing between two guys who are just connecting. And so to recognize now what's the context. So these are deep learning models. They can put lots of context in. So now you need to know the context of who's talking to whom where to understand whether in fact that's appropriate. You don't expect when you're talking to your friends over a drink, you're going to talk the same way that when you're slacking at work, right?
But there's lots of really subtle bonds. Not like I can say very mean things with very, very acceptable words.
And hopefully the deep learning will get better at trained at doing that. You know, I'm not claiming it's solved. I'm claiming it's not solved. All I'm claiming is a lot of people I talk to, both in academia and in industry, are spending a lot of effort trying to figure out how to put that signal in so the gradient descent moves it to be a little friendlier.
No doubt.
Finally, the piece here that's hidden under this bar, which is very annoying, is, oops, let's see if I can.
You can move the bar.
Okay, move the bar. Is I think the piece that looking in the future, personally, and I'm curious to hear what Conrad thinks or disagrees with me. Personally, I think that what we really, really need in deep learning is much more integration with external data sets. And as a brain guy, you'll appreciate that most of your brain has, maybe you'll agree, really good fast retrieval of data. Associative memory, pull lots of data. You're really good at remembering stuff. And it's not the case that you want everything remembered in a single deep learning network. If I ask the question, what time is it right now in California? That's unlikely to be in Google's training set, right? Or
well, it's in Google's training set, just wrong. When it was written, isn't now.
Well, many, many versions of the time in California exist in the training data. But in fact, the way to do that would be to say, do a Google query, type to the web, what time is it in California? Take the answer, which is actually quite accurate. Google's good at that. I actually worked on that when I was at Google. Works really well. And now you want to feed that back to the neural net. So what we want is a neural net that takes a question from a human, like a conversational agent like Lambda there, and someone asks it, what time is it in California? It should know enough to know that it should generate, with a standard transformer, a query, send it off to Google, take the response, feed it back, embed it, feed it back into the network. Does that make sense? And there's a ton of stuff where you want to store facts about the world, right? If you ask Google, what color is Conrad's hair? It shouldn't be just trying to remember what the neural net knows. It should have very specific information, either retrieved by querying Google image search and looking at the images, or by actually knowing the fact that you knew it from before and stored it.
And I mean, facts change. A
Facts
query
change.
based on the past data, what's the relationship between Ukraine and Russia?
Right.
Will give a very different answer than the answer we would want to have right today.
And neural nets are surprisingly good at doing basic arithmetic. You can actually take a standard transformer and it will do simple arithmetic. But for complex stuff, as the digits get longer, it gets more and more fuzzy. Why not do as Google does here, have your neural net call a calculator, hello, which of course Google also has. So that's another Google search. Call a calculator, find the result, output it, right? So to build in these facts, somehow we've tried to put everything inside the neural net. And I think that's deeply wrong-headed.
Right.
Cool. So that's sort of the big pieces. So where do I see things as going? Trying to link deep learning to external data, to knowledge graphs, to descriptions of here are movies and reviews. Questions? Yeah.
Yeah. So on this one, I saw a post by Yanni about like small data sets, sort of like somewhat similar, like smaller data sets combined with like pre-trained models. How does it sort of like relate to this?
So I think in always, for lots of cases, you're going to have little data sets, but you'd like to have a neural net that learns in general a mapping from some sort of input from a human. Where will Robin be next Tuesday? To something that then takes that, translates that to something which could be a SQL query or a calendar query, right? Executes that query against your little calendar, pulls out the results, and then generates the text with a GPT-3 style. But note that many of these queries in the real world are going to be against tiny data sets. Your calendar is not a big data set by Google standards, nor is it one that you necessarily want globally readable, right? Certainly Google will not share your Google Calendar every day without your permission, but it is the case you want your deep learning system to know the facts about you, to use your contacts. If you look at modern speech recognition or machine translation, the good speech recognition systems like Microsoft Skype's grab your contact list and use that as an input to their deep learning speech recognition, right? Because it's really hard to spell all your friends' names right unless you have a list of them. Almost impossible. So lots of these systems are now trying to tie to very small data sets, your contact list, your calendar, and then incorporate that in a general methodology of having conversations or answering questions.
And Lyle, I want to argue that this calling specialized data sets,
Yeah.
specialized modules, is very common in our human experience of the world. You know, like you can say, the kinds of things that feel like a neural network are the things that I get like the answer right straight out of it. If you're Conrad, what's the day? That's totally not what I'll be doing. I'll be like, okay, let's see. On Sunday, I filled out my tax forms. Therefore, it was 4/14. And then it's been like, and I go through it in like this episodic memory of I have like, okay, one day, it must be the 12.
So semantic memory, episodic memory. What's episodic memory?
So episodic memory is the memory from which we take the sequences of what we did. Now we can all like in our head kind of say, okay, what did I do this Sunday? And I'm like, okay, then I went with my family and we went to this place and we like, and it has like this whole memory of the sequence of events that we did.
And so the deep learning we've done is all semantic memory. It recognizes faces It understands English or Mandarin or Hindi. What it doesn't do is have autobiographical memory. It doesn't remember what you had for breakfast this morning. It doesn't remember the sequence of personal events. It's missing a whole kind of memory.
Yeah, and for example, if I ask you to do arithmetics, it's not that you pull it out of your like implicit knowledge of language. So in that sense, like we shouldn't expect transformers to be really good at that.
But they are pretty good as long as the digits aren't too big.
As long as it's very small, and then
And that's how you do that's how you do language. If you're learning the times tables, 5 times 7 is that one you've just memorized it like a transformer.
That's right. But if I give you 2 large numbers to multiply, I'm like, okay,
There's no way I can look at it and just get the feeling. Yeah.
And it takes me time, and like.
And the transformers are remarkably good, and they make funny mistakes like forgetting to carry the 1 when you do the additions, and little things like a human might make who is not actually really doing it.
Yeah. So, but I think that this like work with heterogeneous systems is definitely something that systems will be incorporating, in parts because we do.
And I think when we teach the course in 3 years from now, I think we'll be having our neural nets do outside SQL queries or Google queries.
Yeah, it's essential.
I just don't see how it's really going to do stuff. The other piece I think we're missing is sort of longer scale chunks of things. That the stuff we've done is all, here's the input, boom, it goes the out. And so many things we do in life, you're writing a paper, you're writing your final proposal, there's a whole bunch of steps that have to be taken. And somehow I don't really know how we should glue these things together.
Yeah, people will figure it out. You will figure it out.
Hopefully you will, right? Cool. So let's talk about a few more concrete examples of the future.
Yes, in fact, let's look a little bit at some equations there.
Equations, cool.
Do we have a laser pointer? Probably not. Okay.
No.
So this is an equation that you all know from machine learning. Now, like here we have the risk calculation for a given hypothesis, interpretation of the world, if you want. How do we calculate that? Well, we go through all XY pairs according to their probability distribution, dpxy. And then we have the loss associated with the hypothesis applied to X. Now, like the hypothesis here would be, say, the neural network. We have the neural network produces h of X as output, h of X and Y jointly defined.
So this is the expected value of the loss.
That's right, yeah. This is just the expected value of the loss,
Cool.
the risk, if you want.
Risk, right?
All of machine learning, or almost all of machine learning, tries to minimize risk, and empirical risk minimization is the theoretical framework that we generally use when we do machine learning. Now, let's see how that's overall defined. Now, like we have a trained training set and we have a test set. In traditional machine learning, we assume that the train and the test set are drawn from exactly the same distribution. We assume that they're drawn IID. So what do we have there for the expected risk here? We have the integral over all possible training sets of the risk associated with it times, and then we have to integrate over that probability distribution. Now there's going to be certain stimuli that are probable, certain other stimuli that are less probable. High risk for the probable ones is worse than high risk for the improbable ones.
By stimuli, you mean the X's we put as input to our net, right?
Yeah, the X is the input to the
You're
net.
setting like
The
a
Y is like
psychologist.
the output, the desired output of the neural net, of the net. H of X is what the neural network does. Okay, so this is the expected risk here. You have to integrate over all possible training sets, and then you have the risk, and you have to integrate according to the probability distribution. Now we can, of course, rewrite that and basically put the previous equation that we have here for the risk all in here. So now we have an integral over all possible training set, an integral over all possible test set. We have the loss that links those two. We have h of X and Y. We have the distribution that we train with, and we have that we test on, and then we have the distribution that we train with. So this is what we've been doing so far. Now, like this, you might not be used to this notation, but it basically just says that empirically, we can approximate these integrals by sums over samples that we get from both of them. That's what we practically do. And then we can therefore have our empirical risk expressed like this. And why do we need those two integrals? It could be that the world solves this really weird data in our training set. And yes, that happens. And it could be that the world solves us really weird data in our test set, and that happens. So therefore, we need both of them.
Well, when my students, at least who took 520 with me, we talked about bias variance trade-off, and we worried about if you have different test sets, different training sets, you would get a variance in your outputs, because every different training set is going to give you somewhat different results. So at least in the classic 520 sense, we worried a lot about this, but we always assumed the test distribution was the same as the training distribution because we lived in math land rather than reality.
Yeah, which is what we assume here. It's like the same P of XY
right
from the test and from the training distribution. Now, reality doesn't look like that. In reality, every application of machine learning is always out of distribution. So we get one training set, and then ultimately our data set needs to survive in a different situation. Typical examples, we have images from the past, and we want to properly classify things in the future. We have
everything. We have data from the past. We want to predict the future. Predicting the past is mostly sort of boring, isn't it?
No, exactly.
At least all companies I know would like to predict the future.
No, this is in empirical risk minimization. It is about predicting the future. It's the same distribution. We assume that both the data we train on and the data that we test on are drawn from exactly the same distribution. If they are different, then things look very different. Now, like here's the risk in the out of distribution case, where we have now we have a probability distribution over the test data and a probability distribution of the trained data. Now we integrate over the trained data, but we also integrate over the testing data. This is all the things that could happen based in the training set. This is all the things that could happen in the future test set. And then we have the loss on the test set, because that's what we learn about. Like I learn right now about something, but I'm always about predicting something later in the future. Out of distribution just means those two distributions are different. And then, of course, we have the loss in the future of what will happen with the hypothesis that we learned in the past on X and on Y, and we have to, of course, integrate over both of them. Okay, so out of distribution, now like what makes this complicated is we have this different distribution over the test set. And now the failures of deep learning generally come from the setting. Why? We train on something. Now, like it's easy to not be wrong if we test on the same thing. We all know the mechanism for that. That's what we taught you the entire class. The thing is that in practice, the future is always different. We test on, say Lyle mentioned the medical case. We want to predict which drugs will be good. But in practice, in those cases, the drugs that we train on are drugs that have been used for some reason. For example, they might be small molecules or something like that. And now we want to predict what happens if we go into a different domain, like usually bigger molecules, usually molecules that are not produced by biological agents, which are in our training set massively. And in that case, we have a real problem because all the guarantees, all the cool thing that we've been doing doesn't apply at all in principle if the future is different from the past.
Well, and sometimes the world's even worse. It could be adversarial. I was talking to the woman who won the Alexa Prize with her CMU team. They trained up a conversational agent on a bunch of nice, friendly mechanical Turkers and people that did it. And she was demoing it in a high school. And it took about 2 minutes for the boys in the high school to get her chatbot blocked by Amazon because it started swearing back at the boys that were swearing at it. So it turns out adversarial high school boys, she said they were boys, are quite able to bring down a system with a very different distribution of prompts than you get from a normal paid grown-up professional tester.
And let me zoom out for a second. Over the next few slides, I will tell you about the nature of how the future relates to the present. And out of that, we will get a whole bunch of intuitions on how to build engineering systems that work well. Okay, so that's the problem with out of distribution, that basically fundamentally the future is different. But in reality, the future isn't arbitrarily different. So you can say we have the probability distribution of the future and the past, and they are coupled. There's not one probability distribution for the future that is entirely different from the probability distribution of the past. If it was there, you couldn't learn anything about the world. But in reality, probability distributions that you have in the future are in a way similar to probability distributions that you have right now. And so let's go through that. We have to still consider all possible past data sets, all possible future data sets. We will have that same loss, but now our integral is about the future depending on the past. No? And so what things do you think are coherent over time? What are the things that I can learn today that are still valid tomorrow? And why? Now let's think about the world. What are the things that we can carry into the future? Yes. Yes, why? Yeah, that's right. Now, like there is a causal underlying model with which humans produce actions based on their inputs. That causal model is unlikely to change radically over a short period of time. My behavior tomorrow might be very different. Maybe like you come to my office and you're like tell me lots of horrible things and I'll act differently. But it's still the same kind of underlying model. So you can say there is something about a conservation of the causes of things that carries through very much, but the inputs change to a system. And in that sense, like you can say the things that are really shared between the past and the future are the mechanisms that are invariant, the mechanisms that kind of describe how the world works.
I think it's also true at a much more superficial level, at the input level. The correlation structure between pixels is fairly standard. Closer pixels are more correlated, so embeddings from images work well. The meanings of words change slowly a little bit, but by and large, words in English today, most of them, 80%, mean the same as they meant 50 years ago. There's a lot of stability. So at the low level, particularly perceptual processing, I think, sounds that are closer in time are more correlated than sounds that are farther away. So these embeddings that we learn, often we share across lots of models because the features that you need for edge detection really are quite stable.
Yeah, so the interesting thing is, like in a way, a lot of these invariant mechanisms, we build them into our deep learning model.
Right.
No, so when we have a convnet, why do we put in the convolution? We put in the convolution deep down because we believe that the mechanism, let's say, makes the image of a hand is a mechanism that will be shared across space and time.
Well, and it's translationally invariant.
And it's translation invariant. But like this insight of translation invariant is in a way something that we should discover, that we shouldn't have to build in as humans. So in that framework where we ask about what's the expected future loss, our question gets to be, what are the things? What are these mechanisms? What's the causal mechanism in the world that will carry in the future and still be equally relevant as it is right now? So let's think a little bit about how the world relates to the past. So you might be inclined to view this as just like the way we think about reinforcement learning. We don't. What we have here is we have two different time steps. Think about them as tasks. Right now, I'm giving a talk. This weekend, I might go hike with my family. What are the things that I can learn from giving a talk right now that will carry over to hiking with my family? No, because if it's not, then like I could only learn very narrowly for doing the same thing again. But that's relatively useless. If I learn something just about talks, well, I don't know how many talks I'll give, but it will be very local. I want to be able to generalize it. But I see you here in 3D. So that's at least something that I should be able to carry over. Not like the world is made out of people. Okay, I see them here. I have mechanisms to detect that that is one of these causal mechanisms that's carried over. So now let's talk about like these task situations. What's going to happen from one task to another? Like I'm in a certain world right now. I will be in a version of the world that we have a later point of time. Let's call these W here. Like WN, W now, what the state of the world is, and WF, what the state of the world is in the future. Now, what can we say about these two worlds? Well, they will, for example, share the same physics. Anything I can learn about physics in this room, and there's plenty of it, like stuff falls down, sound waves propagate, Conrad walks. There's kind of all those things of which I can very strongly believe that they will still be the case. And then there's other things which is say, Lyle is here, and you're here, and you're here. Those will not be the case when I go hike this weekend. So there's going to be certain aspects of the world that will change very much and others that change very little. And now you can say, what's going on in every one task is like the world makes the stimuli that we have. The stimuli decide with my hypothesis what I'll be doing. And what my hypothesis, what my interpretation of the world is. And I'll use this to produce actions Y. Now, let's talk about the 4 things that I think deep learning is really, really bad in this context. And so the first one is, of course, constraints. And we've been building them in more and more. Like translation invariance is a constraint. It's just one that I would have liked to learn instead of building in. But you can say I have constraints where I say I have certain priors over which learners I want to use. G is the learner that basically updates my internal state over time. And I have priors over the state that I will be representing the world in. So those are constraints. And I think the way we do them at the moment in deep learning is relatively ugly, which is they all come from humans. Like that's what we do in the design of a neural network. We build in the ConvNet, we build in a transformer. Why do we build that in? In an ideal world, I'd want to explain my world to you, and you just tell me which deep learning algorithm I should use. There should be a way of compiling knowledge about the world in terms of constraints, and that then translates this knowledge about the world into the right machine learning algorithm. Why is it that it always goes over our desk? In a way, it's clearly wrong. You should describe to me how the world is. You shouldn't build a deep learning system. And I think we will see a lot of progress in that area. So what else do we have? The second one is causality. If you try and understand the causal parts of the world, they're very likely to carry over. It's about mechanisms, not like physics. I want to learn about physics. I don't want to learn physics specifically about microphones. I want to generalize that. So therefore you can say, there's lots of ways how which I can successfully describe the world. But what I want is that if in the task that I have right now, giving a talk, that what I learn in that task carries over to a task in the future, hiking with my family. And the mechanisms, the underlying causal chains, I can expect them to carry over. For example, I can make someone angry by like saying something bad about them. Like, I don't like the color of your t-shirt. And my family would be angry. You would probably be angry if I disliked.
So arguably, Conrad, our current architectures are hopelessly inadequate for doing that, because our current neural nets don't represent anger or t-shirts or families. All I have is a bunch of pixels or characters or sound forms going in and some prediction going out. Maybe we'll get back to this later today, but doesn't it require that we then actually have neural nets that learn about t-shirts and anger and what I would call concepts, that they make these things as sort of symbolic nodes that
Yeah,
mean something as opposed to this big unwashed mass of distributed representation?
Yeah, so the kinds of things that we effortlessly do are almost completely missing, which is a neural network can't tell you those are the variables that you can intervene on that causally affect the future. And every human being has that.
But they don't have variables. So do you think we have variables? Do you have, I mean,
Well,
you don't have a node for anger sitting in here anywhere.
well, I don't
The
know if you
amygdala,
have
maybe?
a node in your brain, but you certainly can reason about that. Not like,
Yeah.
when this thing happened and you did this thing to me, you have like, yeah, he's kind of gonna be slightly upset, but like he'll be fine or something. Not like that's the kind of, we all have that kind of reasoning, and we use words for that. And so we certainly have that.
So so I guess that's a question. I think a big open question in deep learning, how much do we need things like words for that, which take things out of the normal distributed representation and make concrete objects like t-shirts and anger that we use words for reasoning? And how much do we actually just have a sense that, oh yeah, she's going to be pissed without putting words on it, that then could maybe be done within this current purely distributed representation?
Yeah, so I'm not sure how important words are for that, but let me maybe give you another reason why I think causal thinking is so useful. So in the world where humans are, in the kinds of tasks where humans are very successful relative to other species, we are often in that situation where causal interactions are very sparse. Now, in principle, I have like 1 million pixels. All those pixels jointly do something. And in a way, a neural network views the world like that. There's like all those pixels, and we're trying to learn some relationship to it. But in the world in which human logical thinking happens, here we have 20 students in there. There's people that I talk to, people who will ask me questions. There are people who will be looking at things. There's people who will be reading emails. But in all those things have logical meaning for me, and I reason in terms of them. And if you put me into a situation where things are very diffuse, everything interacts with everything else, I will fail to be successful. So you can say that the defining feature of the human niche, the kinds of place where we are very successful, are those where causal interactions are extremely sparse. And a lot of what we do in engineering is we make them even sparser by like coming up with like principles behind things that carry over. And so in that sense, discovering the world in those terms where the interactions are sparse is going to be important for neural networks if they're eventually going to go towards human type intelligence.
I agree. And I think when I look at sort of the luminaries in the field, the Jeff Hintons and the Jan LeCuns, they're all arguing for some sort of a modular architecture. It's just not tractable to have every neuron connected to every neuron, even within each layer, even at a CNN. There's got to be some sort of a higher level structure. And what that is, I think, is the open question for the decade, maybe.
And maybe to give a little more background to that, the leaders in the deep learning field are today all getting excited about causality. Joshua Bengio writes lots of papers. Jeff Hinton writes lots of papers. Bernard Shulkov does writes lots of papers about causality. I just a month ago had a wonderful workshop with a number of those guys thinking about causality. How can we learn from the world that is so complicated to describe it in terms of things that have causal interactions with one another? And it's also from causal knowledge is also, like one advantage of causal knowledge is it will be good at carrying into the future. The other advantage of causal knowledge is it describes what I want to do with it. Like the world has a limited number of interactions, not like words primarily here and how I walk around on stage. So there's a very small number of like levers in the world that I can move. Discovering those massively cuts down the search space of what I could possibly be doing, what would be possibly meaningful answers to it.
And in some sense, reinforcement learning has been a limited success because the models are too unconstrained. They don't have enough explicit representation of causality and sparsity, and therefore they're slow, extremely slow, because they don't have this sparsity and this representation of causality, right? They're learning, the RL is learning a causal model. It's just not a very good one. It's a very general, sloppy one rather than the structure and the sparsity.
Yeah, and half of it is built in by humans. Now, like if we talk about Go or something,
yeah,
we give you a list of what things you can do.
Which is why it works so well.
That's why it works so well. But Monte Carlo tree search basically has the humans built in a notion of causality, how the futures can unfold based off where we're now. So yes, causality from my perspective is extremely important. And it is graded. Now you can say it's almost continuous, where I can describe the world in more and more meaningful causal variables. And us as humans have a very peculiar notion where we have a very sparse set of things with interesting attributes that interact. So, but there's more. Wait, there's more. So you can say that the bias towards causal representation makes the error from the world now to the world in the future more consistent. Because otherwise, the world can be divided into things that are just state and things that are mechanism. The things that are just state will change. And the things that are truly mechanism will remain invariant to the level that mechanism is physics that will, as far as we know, stay constant forever.
Well, sort of definitionally, if it's not, then your physics is wrong.
And that may happen. Or like
Physics could be wrong, but yeah.
Physics could be wrong.
Has been before.
Most things aren't final. So that's the important thing about causality. Now let's talk about curiosity. What can I do right now that's helpful for the future? Well, I can learn good. That's kind of like the baseline that we were talking about. But I can also do things to learn something about the world. For example, if I want to get at causality, I can poke things. It's the only real way with which we can be sure that we understand the true mechanism in the world. Could be a movie in principle otherwise. But because we can interact with the world, we can know something about how causal chains are. And so curiosity is, I can do things right now in our current task situation that are not meant at making me good at the current task situation, but that are meant at making me good in the future.
So we have a name for that in reinforcement learning.
Mm-hmm. What's the name in reinforcement learning for that?
Exploration, yep, people said it.
Yes, okay.
And I think it's worth noting, Conrad, how this is different, what you're proposing, your curiosity rebranding of the exploration that we mostly do in contemporary reinforcement learning, because most of the current systems are, for example, epsilon greedy. And what do? They're not very smart at figuring out what to do, right? Your curiosity is, I think, much more targeted in an optimized fashion, as opposed to trying all possible things or things that are at least somewhat sensible, but not as aimed. Question, comment?
In this sort of paradigm, you have to potentially have a piece of itself within assess a certain action or like various exploration.
Yeah. Yeah, so maybe let's dig a little more into how the difference is to reinforcement learning. So what do we do in reinforcement learning? Let's say we are playing Go. Well, sometimes we will choose a move that is slightly suboptimal, because that way we will learn that maybe it was optimal. We were just uncertain about it. So we are basically, if we're in a traditional reinforcement learning situation, we are on the task doing it, and we explore a little to like learn how to do this task better. But that is not at all how like animals and biological beings do things. So if I take a hungry mouse, put it into a new environment, there's a piece of cheese like right next to the mouse. What's the mouse gonna do? No.
Hungry, depends how much hungry.
Depends, yes, if it's dying of hunger, yes, absolutely.
If you take a random rat and throw it in a maze, that's very different from a hungry mouse next to some cheese, I think.
Exactly, it depends on the exact details of that. But like, if animals get into a new environment, what they do is they explore the environment. They're not trying to solve the current task. So a rodent put into a maze, even if there's food in it, will first try and explore, okay, like where's it going? Where can I go? Where could I hide? In other words, the rodent is preparing for different tasks. And that is how this is different. Now, like in reinforcement learning, we are playing with things. Can I get better at throwing this ball or something? In learning for the future, we're like, in the future, I will have different tasks. There might be someone who wants to eat me. There might be a lion. There might be, I might become thirsty. I might want to play. Like there's all those things. And we are always, the curiosity that biological agents have is not the curiosity that a reinforcement learner have. Let me get better at like eating this cheese a little faster. Instead, it's like, let me figure out what I could do when the world changes because I know that the world's going to change. And so in that sense, this curiosity is something where you abandon your current task for a little bit to figure out something.
One of my smartest friends, when he's doing anything, we're playing mini golf, and half the time he's like hitting the ball, and half the time he's taking the golf club and measuring how deep the water is. When he plays video games, sometimes he's trying to win the game. Sometimes he's like, oh, what would happen if I tried to go through this out of bounds? Right? Just this exploration. And so much of our current reinforcement learning and all of deep learning, immediate piece here, rather than creating artificial, purely internal subgoals. Let me see how far I can run. Let me see how fast I can run. There's no external reward, right? Reinforcement learning is all about maximizing external reward, whereas I think curiosity is about creating internal rewards where you can watch a baby trying to put their foot in their mouth. And that's a rewarding thing somehow, even though there's no external reward for putting your foot in your mouth. But if you do it long enough, you learn something about mouths and feet, which apparently is quite fun if you're a baby.
Yeah. And also, it again has like this link to causality. Now, like the baby mouth and the foot is kind of, what can I do to my leg? What is the underlying mechanism of muscle commands I send to what my body does, which is going to be invariant. Now, like I haven't like tried to like bite my foot in a long time, but I think I'm like, I probably do like this, and I might even still succeed. And I learned that a long time ago, and I have like this model therefore how causally my body works. And I think that that is super important, that link there. The other thing is, without action, causality is kind of impossible. You cannot find out how the world really works unless you really interact with the world. But that is a different course. I've been teaching causality for a while.
But they're merging.
The last thing is that is an important factor is continual learning. So neural networks tend to catastrophically forget. You teach them something, teach them something else, they lose what they had first. People and animals just absolutely don't do that. And why is that? Future worlds contain the same things as past worlds. So technically, really forgetting things is an actual mistake. It's just a mistake that we can't formulate in terms of gradient descent. Now, like, what does it mean that like we forgot something?
Well, the problem is this global model that you've learned a bunch of things, and when you see something new, you take all the weights in your whole model and you gradient descent them. which is completely wrong. If you had sparsity and structure, when you actually put your keys somewhere, you should be gradient descenting where the keys are or remembering them and not changing your model of how your foot works, right? So this, again, this global model that neural nets have is supremely wrong.
A lack of structure.
Right.
No, and so let's maybe just briefly like wrap these things all up together. Learning in the real world is about performance in the future based on where we are right now. It is not about IID settings. And arguably in machine learning, the IID setting is starting to be boring. If the future is just like the past, like, yeah, we can generally solve that if you just give us enough data. But there is this illusion in the field that we can just solve things, you know, like that basically if our transformer is just big enough, trained with all the human language in the world, it would be good. Well, imagine we could train, in fact, we kind of have, on all the written language by humans. It could still not tell us that Ukraine and Russia are at war right now. It couldn't even like tell us what the probability is that something like that would happen. So basically, the big mistake in a way in the machine learning setting so far, and that no one has solutions for, is that the future is different. And if the future is different, you get like 4 things that are fundamentally helpful. The first thing is constraints. Like if you tell me things about the world that will be true tomorrow, I should use them. And in that sense, that goes beyond data. And you have 1 billion lifetimes of human lives in you that help you know what kind of futures you should expect in the future. And that's, in that sense, constraints are incredibly useful. But also the things we do right now. Most of the things you do are about curiosity, you know, like why are you at the university? Why are you studying? No, you prepare yourself to do well in some future scenario. That future scenario is like totally different to where you're right now. And yet you somehow have this intuitive notion of what the things are that you need to learn to be successful in your future. So curiosity, doing the things now for a future that has never yet arrived, where you don't even know what the exact task will be, you know, like who knows where you'll be, who knows what exactly you'll be doing. But you're trying to pick up skills, knowledge, causal knowledge about mechanisms that will still be relevant at that point of time. And learning, deep learning is just one mechanism. And then, of course, of all the explanations of the world, we want the causal ones. And in any representation, we expect aspects of the world to reoccur. And therefore, we want a representation that is there. All of them point into a direction. We just want a more structured, more meaningful representation of the world than the one that we need for the past. And it's really, it pushes us more into the symbolic directions, more in the causal direction. Because the other features of the world, they will evolve over time. Everything will be different, but certain things will stay the same, and we need to figure out what those are.
Question.
Yes, plenty of them.
And I'll talk later. I've got a couple examples of a little bit of architecture.
Okay, then why don't we go to your architectures?
Yeah, I mean, I think those are the next slides, right?
Your slide deck, it comes afterwards here.
Yeah. So with that prompt, I have stolen from Henry Kautz, who's a NSF program director, a recent talk, March 2022, slightly modified to fit my style, of looking at what's called neurosymbolic reasoning, which in some sense is the jargon term for a lot of this, how do you build structure in? And if you think about most of the worlds that we've currently looked at, we look at something that often is symbolic on the input, a document with words, characters, symbols in it, and something output, some label, the sentiment or the classification or the translation to Chinese or whatever. Or you take something that takes in a symbol, a set of sequences, an equation, and outputs something which is the integral of it, or the derivative of it, or some sort of evaluation of it. So a lot of neural nets currently do things that handle symbolic in and symbolic out. but everything we've done in this class has a big no symbolic in the middle, right?
Okay, question. Why is it continuous in between?
Oh, good question.
No, you've all been doing this. Why? Why don't we stay in symbolic land?
There's one magic thing about continuous functions. Sorry? Gradient descent. Yes, they're differentiable. They're gradient descent, right? So our whole deep learning world relies on gradient descent, which really sort of relies on things being differentiable and continuous. And frankly, as someone who's been doing deep learning since the 80s, I'm astounded that you can represent things as discrete as English to Chinese translation in a purely continuous function, right? These functions that we have are remarkable. They take something which is a highly nonlinear discrete function and approximate it with a fully differentiable one, end to end, right? English in, Mandarin out, and take derivatives and optimize it. This is phenomenal.
But let's be clear, are we losing something on the path there?
Well, we're losing all of the substructures. We have no knowledge. The old days, they used to have grammars built in that actually knew about nouns and verbs, that actually knew about the relations between the different components. We're losing lots of structure.
Yeah, no, like to make the point, no, before deep learning, people did good old-fashioned AI. In good old-fashioned AI, there are lists of truths. And we can say, is this true or is this not true in that discrete framework?
But let's realize why it is that places like Google drop that. Fred Jelinek at IBM famously said, every time I fire a linguist, my machine translation performance goes up.
That's right. Why?
Because what's wrong with the old-fashioned version? Why did symbolic AI not win? You have to hard code it in. And how big is the grammar of English? The largest grammar I found is 6 volumes, and it's incredibly incomplete compared to the standard code inside of Google Translate, right? That 6 volumes of English really doesn't capture, make up, make over, make with, make out, make up.
But Lyle, I didn't want to just make this as a point for neural networks are better. I believe that there's something really lost in that translation.
There is something lost, and it works moderately well on 99% of the text that you have in English and Mandarin, where you have billions of words. It becomes much harder on the 1% that you're missing the tail, and it becomes much harder if you're in Hausa or a lot of other languages where you just don't have that level of data.
But it's also very hard from this to say extract a mechanism or something.
It's hard to get a mechanism. It's hard to be reliable.
Grammar, you can say,
right,
if A, then B implies if not B, then A.
Yeah.
I cannot say that that readily in
no way. The inside is all your convnet or your transformer, right? It's all magic. So what have people done? Well, one early thing we saw is, in fact, last week or so, is to do something that says, I'm going to play Go. I will have a neural net that learns something like a board game evaluator or a policy, and we'll build in, as Conrad said early, some hand-coded Monte Carlo search. I don't think that's a terrible idea. I mean, you seem less happy with it than that, but I think it's...
Oh, I'm not unhappy. It's just something that we built in that the system doesn't learn.
Right, and here's the deal. If there's a small number of things that we need to build in, like Monte Carlo tree search, we will do okay. Or translational invariance, if there are thousands of things we need to build in, then we're going to lose, right? And somewhere in the world is people trying to build in, there are people that are masks, their glasses, those sort of approaches have failed because there are just too many of them. There was a guy, Doug Lannett, who spent 20 years with a team of 20 people trying to code all of knowledge. And I remember him coming here to say, oh, about 20 years ago, he was here. He said, oh, we're going to do this. We'll have machine reading that will do this automatically. And he had people who spent like a team of 20 a whole year doing a biology textbook, all the facts built in. It was super cool. It was a lot of money. Never really worked. Psych, it was a great project. And it failed miserably because there's too much stuff. So I think some things it's probably not bad to build in, like the idea of search. and some things like what's a wire, just a wire, too many things to build in. So that's sort of one approach, classic. Another one, which I'm less in favor of, but some people have tried, is to say within the neural net, I could build in a structure. So if I have something that says, I've got some idea about what the functional forms of things are, I could build in stuff that says that we'll have a bunch of internal structure of how to build the network. Why do I not trying to like coding in these sort of, why might I not like coding in the structure inside the neural net? I'd rather it learned it itself because I don't know how to build the structure in, right? This is in some sense the thing that failed in AI the first time, was trying to build in lots of internal structure. But people are trying. Ones I do like, is Josh Tenenbaum stuff. Take something that takes in an input, say a video of some little squares bouncing around, runs a CNN that then maps from those continuous pixel inputs to some discrete object recognizers, matches those to some sort of words like questions. So there's an input which is a video, an input which is a question, literally. What is the shape of the red object left of the sphere? Learn some mapping between red and left and sphere, and then is able to translate the question and the image into the same sort of logical space, right? So you have a logic thing that says that the question gets translated to query, shape, filter, red, relate, left, filter, sphere, which then gets tied back into the embeddings. So you have a full system that sort of maps images to objects, spheres, shapes, which have properties, color, shape, location, speed, and relations. Yeah.
Are there multiple concept embeddings? So you'll choose there's like maybe 10 embedding layers set there to like embed what the video is, or is there one that
There's a, well, it's a multifaceted thing in the sense you're doing object recognition, that you're segmenting the world into objects, blocks, chunks of things, entities, and then those entities get assigned properties. Properties are things like color and size and shape and location and speed, so that you're building something that exact architecture. You could do a bunch of, normally you want probably some shared underlying layer, because after all, the properties like color, a color recognizer should be true for every object. And the shape ties to the location, the size, right? So how to exactly do these, I think we don't know. And in some sense, I don't say it doesn't matter, but it's not obvious what the right way to do it. But I think the fundamental notion that's important is this tying between this rather different spaces. And I started the talk today by saying people are moving to multimodal systems. But the big multimodal systems that take in video and text do not work like this, right? What's fundamentally different about this? It's explicitly representing this is a world with objects, and getting a representation where once you have the objects, you can send it to a physics simulator and talk about things bouncing off each other, where you can actually ask questions about them, not in the sense of question transformer full embedding, but question mapped to a symbolic representation that is the same space as the symbolic representation of the images.
this word for saying what is the velocity of the red ball?
Yeah, absolutely. What's the velocity of the red ball? Exactly the sort of question it should do. It should be able to find a red ball, try and decide there's one of them as opposed to two of them. And then it would have a property, which is velocity, which it would extract.
So I just wanted to point out how it relates to what we had before. Now, like before we had symbolic, neural network, symbolic. What they are basically just doing is go symbolic, neural network, symbolic, neural network, symbolic, neural network, symbolic. They basically have basically mixed these things. So they go from text to a neural network to text basically to a query language. And then they go from the image through a neural network to an object descriptor of the image, which again is like a built-in structure there.
I have no idea why the image on the screen is not representing. My computer looks beautiful, but we'll ignore the fact that there's no image there. So I think it's worth noting, what's the downside of the hard part of these things? If you're going to have to actually hand code in what objects there are and what attributes they can have, you're back in old-fashioned AI. Yep. How do we create the symbolic representation of text? That in some sense is the fundamental problem here, which is that either you've got to build in, there are objects, they have shapes, they have colors, in which case you probably have something that's not really scalable, or you're going to have to actually start to view that the language itself is the qualitative. So there are words like shape and red and sphere. So arguably language already produces a discretized description of the world. And you can start to build representations that do that. Now note that there's a tricky part. In the embedding space, red should be sort of close to pink or magenta and farther away from black or green, right? So that you want to have something where there's some sort of mapping of each discrete word to a vector embedding, right? Such that girl and boy are close to each other and farther away from frog or giraffe and farther away from chair or rock. Make sense? So you want something that puts things in embedding space, but you also want some sort of a representation that really says that there's Joe Biden or Donald Trump, and these are entities that have properties and locations and speeds and colors and hairs, which may change, but you know. So the trick here is, and it's not at all obvious, how do you make this mapping between a sort of sloppy English in something where in the old days people tried to say, let's do a pure logic. These are the 32 possible colors in the world. These are the 31 possible shapes. But that doesn't work because there's more than 32 colors and more than 31 shapes. So the answer is we don't really know totally how to discretize it. But I think there's some version that says that language somehow sort of gives you at least hooks you could hang things onto. And at least if you have things like a Conrad or a Lyle, that you can then attach properties to those and start to generalize them. But the answer is, this is the state of the art. This is contemporary, one of the best guys in the world doing this, and this is the complexity he can deal with. This is not looking at real scenes with real people, with a classroom full of people. It's looking at little boxes, right? It's still toy problems, completely unsolved.
But Lyle, in this case, I'm not. Are they actually better than other other systems at solving such problems? Not like, what is the shape of the red object left to this?
They're not better at that. What they are better at is questions like counterfactuals. What would happen if I were to remove the purple ball? That's a question that no other system does a good job of asking. And this one does a really nice job on counterfactuals. What if? And to go back to your thing, what do I need for counterfactuals? Causality.
And perturbations. I need to interfere with the world. And you can say, why are neural networks so bad? To play devil's advocate against that. In parts, it could just be that our training set just doesn't have many examples of someone removing the purple ball.
And what Josh is doing here is cheating a bit and building in some basic physics models that says, rather than doing lots of experiments with removing balls in the world, which in fact it could learn what will happen, we will actually, with less training data, but more constraints, in this case, simple physics, be able with a fairly small training set to be able to learn that slightly messy mapping from pixels to objects with properties, then tie that to a nice simple physics simulator, and then also be able to learn a mapping from the not too messy English to a symbol query space. So it's a lot of glue putting pieces together. But I sort of like it.
Yeah, no, it's very cool.
I think it's right-headed.
Right.
Hopefully this moves toward your question. This would be sort of my favorite idea of what's at least a plausible type structure. Cool. So that's sort of the end of the slides. What we've sort of seen here is this notion that says that current deep learning is stunningly good if you've got insane amounts of data and you're trying to predict labels like faces or translate words with labels. It's not really good at moving to different situations, things you haven't seen before. It's not good at things that require large sequences of events. It's not good at rare languages, which you haven't seen. And in some sense, I think we both agree that some sort of structure and sparsity is going to be needed. And I don't think we know what it is because, hey, it's a pretty active field still.
That's right. There will still be enough to do in deep learning for you decades into the future.
Future, right.
That's-
Seems a
that's fine.
fairly safe bet.
I'm reasonably positive about it.
Yeah.
But it will probably not be only deep learning. No, that's the thing here. Like it will need some of that character that people have, where I'm like, okay, you're no longer talking with me because I was so mean to Lyle that he complained to you. Like we can like readily do these logical deductions. And I think like currently we can't build.
And when I
them into
talk to my friends who are doing really high-end reinforcement learning, they're going back to things that feel to me like 1970s AI. They're saying, how do I build something with lots of subtasks? I want to have a reinforcement learning that learns as it plays this game. Here's how to get food. Here's how to stay alive. Here's how to shoot an arrow. Here's how to collect gold pieces. Lots of little pieces, all driven by curiosity. Since there's no intrinsic reward, the reward is winning the game at the end after you get to level 20. But to try and build in little pieces that say, the reinforcement learning will be able to recognize subtasks. How do I learn to move my character left? How do I move my character right? I mean, when you start with the very basic pieces, and hopefully in ways that will generalize in some fashion. So eventually, as they get really good at playing the games, they could then do something that actually will pay money for, like controlling inventory levels in warehouses, which is actually where the money is, as opposed to playing video. Well, there's a lot of money in video games. But this notion of how do you get some combination of building in structure, sub-goals, entities, things, concepts across games. What's a reward? What's food? What's death? What's a life? But those little hearts you get when you play the game, you know, the little ones that go away piece by piece as they chunk them. All those things to try and learn some sort of structure. And current people are building a crap load of it in, or doing really crap loads of learning, right? We don't quite have the build a little bit in that guides the rest of the learning.
Right. And parts of why people are so good is, of course, because we're good at collaborating as a species.
Yeah.
So we have words for things, which for young human kids label the subtasks. You know, like think about like that warehouse manager. You know, like what will they say? Oh my God, we are full, where there's almost no more space. Or like we have a horrible traffic jam at the entrance of like hall number 2. We have all those labels for intermediate tasks, and a lot of what our culture does is produce them.
An interesting question is, should we have deep learning things that write stuff out as English, that produce sentences that it could then later read or store? Maybe. Or should they write to knowledge graphs, which is more common, just triples? It's unclear.
I'd say if we look at Josh Tenbaum's stuff,
Yeah.
why is this a passing language? Why couldn't this have been English language? Like,
I
the way
think it's
weird.
yeah. I don't like the parsing piece. I would go straight from English to simulator myself.
Yeah, and
But I'm not as good as he is, so you know, it's hard.
Well, in any case, like, yeah, plenty of open questions in that space.
Cool. We're basically at time. Any last things you want to say? I want to say to people that thank you all for a great course, and I'm looking forward to see the projects. A lot of them will be online, so Conrad and I can jump in to see some of the presentations. We'll certainly all get together and read them later. And I hope you get lots of chance in your career to use these things. There's a nice record of people graduating from this course and going off to industry and doing like cool projects at cool places. I love to hear about them afterwards.
Yeah, and
That's fun.
also give us useful feedback. We're still tinkering with the course, trying to make it better.
To understate things, major tinkering, redesigning
Yes.
in beta.
So let us know what works well and what could be better.
Great. Thank you. Thank you.
Thank you for being here.
Good. We're still being recorded. Let me get this off the. Good. Still being recorded. Let me get this off the- Still being recorded.